Early in the morning, while most of the world was still asleep, a 45-foot piece of metal traveling faster than 5,000 miles an hour slammed directly into the surface of the moon. Telescopes on Earth caught the flash. A satellite already orbiting the moon happened to be watching at exactly the right moment. And within hours, NASA confirmed exactly what had happened. This was not a meteor. This was not space debris from decades ago. This was a piece of a SpaceX rocket, and its final moments were tracked, predicted, and documented in remarkable detail. Stick around, because in this video, we are walking through exactly what happened, how scientists saw it coming months in advance, and what this impact is quietly revealing about a growing problem in the space around our own planet. And if you want more real, verified space stories broken down clearly, go ahead and hit that follow button now, because we are just getting started. To understand how a SpaceX rocket ended up crashing into the moon, we need to go back to where this whole story actually begins, back in January of 2025. On January 15th of that year, a SpaceX Falcon 9 rocket lifted off from Kennedy Space Center in Florida, carrying two separate lunar landers built by two completely different companies. One was Blue Ghost Mission 1, built by a company called Firefly Aerospace. The other was a lander named Resilience, built by the Japanese company iSpace. Both landers were hitching a ride on the same rocket, a fairly common and cost-effective approach for getting smaller spacecraft out toward the moon without each company needing to fund an entire launch on its own. The two landers had very different outcomes once they reached the moon. Blue Ghost touched down successfully on March 2nd, 2025, landing in a region called Mare Crisium. That landing made it the first fully successful commercial lunar lander mission under NASA's Commercial Lunar Payload Services program, a genuine milestone for the growing private lunar exploration industry. Resilience, on the other hand, was not so fortunate. On June 5th, 2025, the iSpace lander crash landed on the moon after its laser rangefinder failed during descent, an unfortunate repeat of a similar failure iSpace had experienced on an earlier lunar attempt back in 2023. Now, here is where most people's attention naturally moves on. Two landers, one success, one failure, story over, right? Except there was a third piece of hardware involved in that January 2025 launch that nobody was really paying attention to at the time. And that piece of hardware is exactly what we are here to talk about today. Every Falcon 9 rocket is built in two main stages. The first stage is the large lower section that provides the powerful initial burst of thrust needed to get the rocket off the ground and through the thickest part of Earth's atmosphere. SpaceX has become famous for landing and reusing these first stages, and in this particular mission, the first stage did exactly what it was supposed to do, separating from the rest of the rocket early in the flight and returning safely to Earth to be recovered, refurbished, and reused on a future launch. The second stage, sometimes called the upper stage, is a different piece of hardware entirely. This is the smaller section that ignites after the first stage separates, and its job is to carry the payload, in this case the two lunar landers, the rest of the way toward its destination. Once the upper stage finishes its job and releases its payload, it becomes essentially a large, empty, spent piece of hardware with no further mission of its own. Normally, for missions where the upper stage stays in an orbit around Earth, engineers plan for that stage to eventually be pulled back down into Earth's atmosphere by natural drag, where it burns up harmlessly on re-entry. That is the standard, expected outcome for a spent rocket stage like this one. But this particular upper stage did not follow that expected path. After releasing Blue Ghost and Resilience on their way toward the moon, the stage was left behind in a highly elongated elliptical orbit around Earth. For reasons that are not entirely clear even to the experts who tracked it, this stage managed to avoid re-entering Earth's atmosphere during its closest approaches to our planet. Instead of gradually burning up the way similar stages usually do, it kept looping further and further out, and each pass brought it closer and closer to the moon's gravitational influence. This is the point where the story shifts from routine spaceflight cleanup into something astronomers actually started paying close attention to. A rocket stage drifting in an unpredictable long-term orbit near the Earth and Moon system is exactly the kind of object that skywatchers who specialize in tracking space debris keep an eye on, because eventually, orbits like that tend to become unstable, and unstable orbits near the moon often end in exactly one of two outcomes. Either the object eventually gets flung away into a different orbit entirely, or it eventually crosses paths with the moon itself. It is worth noting that this kind of behavior is not entirely unheard of. Spent rocket stages from a handful of past deep space missions, launched by different countries and different companies over the years, have occasionally ended up in similarly unpredictable long-term orbits after completing their primary mission. And astronomers who specialize in this niche area of orbital tracking have had to deal with a few similar objects before. What made this particular case notable was not that it happened at all, but the level of detail and advance warning available once its eventual fate became clear. Because this object could be tracked with relatively good precision using ground-based telescopes, And because its identity as a specific SpaceX Falcon 9 upper stage from a known, publicly documented launch was already well established. Researchers had unusually reliable information to work with compared to some other mystery objects that get discovered drifting in deep space with far less certainty about where they actually came from. On April 29, 2026, an astronomer who specializes in calculating the orbits of objects exactly like this one, named Bill Gray, ran the numbers on this drifting Falcon 9 upper stage and came to a striking conclusion. Based on its current trajectory, this piece of hardware was going to collide with the moon, and Gray was able to calculate the date and even the approximate time this impact was expected to happen, months ahead of the actual event. That kind of advanced prediction gave scientists and astronomers around the world something genuinely valuable, real lead time to prepare instruments, coordinate observations, and actually be ready to watch the impact happen in as much detail as possible, rather than being caught off guard by a sudden, unexpected collision. Word of the predicted impact spread through the astronomy community over the following months, drawing attention from professional observatories and enthusiastic amateur skywatchers alike. There is something genuinely fascinating about being able to predict, down to specific coordinates and a specific time, exactly where and when a piece of human-made hardware is going to strike another world. It does not happen often, and it gave scientists a rare planned opportunity to actually study a lunar impact event as it happened in real time, instead of only being able to examine the aftermath after the fact, the way most lunar impacts are discovered. Then, in the early morning hours of Wednesday, August 5th, 2026, at approximately 2:35 a.m., the prediction came true. The spent Falcon 9 upper stage, weighing an estimated 8,118 pounds, or roughly 4 tons, slammed into the lunar surface at a staggering speed of over 5,400 miles per hour. The impact site was located near a lunar crater called the Einstein crater, on a part of the moon that had been specifically calculated months in advance based on the stage's tracked trajectory. Timing an event like this months in advance is genuinely difficult work, and it says a lot about how far orbital tracking science has come. Predicting exactly when a spacecraft will impact a target as small as the moon requires incredibly precise measurements of that object's current position, speed, and direction, combined with detailed modeling of every gravitational influence acting on it along the way, including the pull of the Earth, the pull of the moon, and even smaller effects from the sun and the way sunlight itself gently pushes on a spacecraft's surface over long periods of time. Getting all of those factors right well enough to predict an impact time months ahead and have that prediction turn out accurate is a genuine technical achievement, even though the object involved was just a leftover piece of hardware rather than an active spacecraft. Let's take a moment to really appreciate the physics of what just happened here. An object weighing about as much as a loaded pickup truck, traveling at more than 5,000 miles per hour, hitting a solid, airless surface with absolutely nothing to slow it down first. There is no atmosphere on the moon to create friction or drag the way there would be on Earth. So whatever speed an object is traveling at when it approaches the lunar surface is essentially the same speed it hits at. That kind of impact releases an enormous amount of kinetic energy in an instant, and NASA officials estimated the collision would carve out a crater roughly 60 feet wide and about 12 feet deep, throwing a plume of pulverized rock and dust outward as debris, what scientists call ejecta. Compare that to what would happen if an object of similar size and speed struck Earth instead. Here, the atmosphere would play a huge role, generating enormous friction and heat as the object plummeted downward, often burning up smaller objects entirely before they ever reached the ground, or at the very least, slowing larger ones down significantly before impact. The moon offers no such protection. Every single object that approaches the lunar surface, whether it is a tiny grain of natural space dust or a multi-ton spent rocket stage, arrives at essentially full speed, with absolutely nothing standing between it and the ground below. That is part of why the moon's surface is so heavily covered in craters of every imaginable size, built up over billions of years of impacts, that Earth's atmosphere would have mostly protected us from. To put that in perspective for anyone worried this might somehow be dangerous to Earth, NASA was direct about this point. A NASA official confirmed there is no danger to our planet from an impact like this, and actually offered a pretty striking comparison, noting that a meteoroid carrying roughly the same amount of energy as this spent rocket stage strikes the moon on its own, naturally, about once every 6 days. In other words, from a pure physics standpoint, the moon gets hit by objects releasing this much energy on a fairly routine basis, just usually not by something we can trace back to a specific launch date and a specific company. What made this particular impact different from all those routine natural impacts wasn't the size of the collision. It was the fact that scientists knew it was coming, and they were ready for it. One of the most remarkable parts of this story is how scientists managed to actually detect and study the impact as it happened, from tens of thousands of miles away here on Earth. The European Southern Observatory's Very Large Telescope, located at the Paranal Observatory in Chile, was pointed directly at the predicted impact site during the exact window the collision was expected to occur. And it worked. The telescope successfully detected the impact plume in real time. Specifically, researchers confirmed the telescope picked up spectral lines belonging to sodium and lithium gas, glowing briefly in the aftermath of the collision for somewhere between 5 and 10 minutes before fading. Here's what makes that detail so interesting from a scientific standpoint. Sodium is a common element found in lunar soil, so detecting sodium in the plume made sense, essentially confirming that the impact vaporized a portion of the moon's actual surface material on contact, throwing it briefly into a glowing gas cloud before it settled back down. The lithium signature, on the other hand, likely came from a completely different source, the rocket stage itself, meaning the telescope was picking up spectral evidence of materials from the spacecraft's own hardware, vaporizing on impact alongside the lunar soil. Being able to distinguish those two different sources within the same brief flash of light is a genuinely impressive piece of remote scientific observation, and it gave researchers real, verified data about the composition of both the impacting object and the ground it struck, all captured from an observatory sitting comfortably on Earth. The European telescope was not the only instrument watching either. South Korea's own lunar orbiter, a spacecraft called the Korea Pathfinder Lunar Orbiter, known by its nickname Danuri, happened to already be orbiting the moon at the time, and mission controllers used that positioning to their advantage. Danuri began its own observations of the predicted impact site about 30 minutes before the collision was expected to occur, and continued monitoring afterward, ultimately capturing a total of 8 separate imaging sessions of the region. The Korea Aerospace Research Institute later released some of that imagery, giving the public an actual look at the fresh impact site directly from lunar orbit, rather than relying only on ground-based telescope data from Earth. Having both a ground-based telescope capturing the spectral flash of the impact itself, and an orbiting spacecraft capturing before and after imagery of the actual physical crater, gave scientists an unusually complete dataset for a single lunar impact event. Most objects that strike the moon do so completely unpredictably, discovered only after the fact by orbiters that happen to notice a new crater that was not there during a previous imaging pass. Having a predicted, scheduled impact that multiple instruments could actually watch happen in real time is a genuinely rare scientific opportunity, and researchers are already using that data to refine how future impacts, both artificial and natural, might be predicted and studied. Now, it is worth stepping back and putting this event into a much bigger historical context, because humans hitting the moon with spacecraft hardware is honestly not a new phenomenon at all. The very first human-made object to ever reach the moon's surface was the Soviet Union's Luna 2 spacecraft, which completed a planned crash landing on the moon back in September of 1959, intentionally impacting the surface as part of its mission. Since then, plenty of spent rocket stages, failed landers, and deliberately targeted spacecraft have ended up on or near the lunar surface, either through intentional planned impacts or unplanned accidents. What makes this particular event stand out is not that it happened, but how precisely it was predicted, tracked, and observed before, during, and after the actual moment of impact. There is also a broader, more important conversation this event quietly points toward, one that space agencies and private companies alike have been grappling with more and more as lunar missions become increasingly common. As more countries and more private companies send spacecraft toward the moon, the amount of leftover hardware drifting in the space between Earth and the moon, often called cislunar space, keeps growing. Spent rocket stages, failed landers, and other discarded pieces of hardware do not simply vanish once their mission ends. Some eventually burn up safely in Earth's atmosphere as planned. Others, like this particular Falcon 9 upper stage, end up drifting unpredictably for months or even years before finally settling into some kind of final resting place, whether that is a stable orbit, a return to Earth, or in this case, an eventual collision with the moon itself. It helps to understand just how different tracking objects in this region of space actually is compared to tracking satellites closer to Earth. Around our own planet, there is an extensive, well-funded network of radar systems and optical telescopes constantly monitoring low Earth orbit, cataloging tens of thousands of objects ranging from active satellites down to small fragments of debris only a few inches across. That network exists largely because low Earth orbit is so crowded and so heavily used by everything from communication satellites to the International Space Station that keeping careful track of what is up there is considered essential for basic safety. The region of space around the moon does not have anything close to that same level of dedicated infrastructure yet, largely because, until fairly recently, so few missions actually operated out there. A handful of independent researchers and smaller tracking efforts, like the work done by astronomers such as Bill Gray, have essentially been filling that gap using orbital calculations, telescope observations, and publicly available launch data, piecing together the movements of objects like this drifting rocket stage largely through dedicated individual effort rather than a large coordinated government tracking system. As lunar exploration accelerates, with multiple countries and private companies planning dozens of missions to the moon over the coming years, tracking this growing population of leftover hardware is becoming a genuinely important area of focus for space agencies. Objects drifting unpredictably near the moon could, in theory, eventually pose a collision risk to active lunar missions, orbiting spacecraft, or even future crewed missions operating in that same region of space. Astronomers like Bill Gray, who specialize in tracking exactly these kinds of objects, play an increasingly important role in identifying potential future impacts well ahead of time, the same way this particular impact was identified months in advance, giving scientists and mission planners valuable warning instead of unpleasant surprises. This event also offers a small but genuinely useful silver lining buried inside what might otherwise sound like a mistake. Because this impact was predicted so far in advance, it effectively became a controlled experiment, even though it was not originally planned that way. Scientists got to test, in real conditions, how well modern telescopes and lunar orbiters can detect and characterize an impact event as it happens, comparing their predictions against the actual observed results. That kind of real-world validation is incredibly valuable for improving future models of how impacts on airless bodies like the moon actually behave. Models that matter not just for tracking human-made debris, but for understanding natural impacts from asteroids and meteoroids as well, information that feeds directly into planetary defense research here on Earth. That last point is worth sitting with for a moment, because it connects this story to something much bigger than a single rocket stage. Every time researchers get a chance to observe an impact event with this much precision, knowing in advance exactly what is going to hit, how fast it will be traveling, how much it weighs, and precisely where it will land, they gain valuable real-world data they can use to check their models against actual results. Those same models are used more broadly for assessing potential threats from natural asteroids and comets that might someday be found on a collision course with Earth. Being able to calibrate impact prediction software against a known, verified event like this one, rather than relying purely on theoretical calculations, genuinely strengthens the tools scientists depend on for planetary defense work going forward. It is also worth acknowledging that stories like this tend to generate a bit of confusion online, especially once headlines start circulating, because a lot of people naturally assume this means an active SpaceX lunar lander mission failed or crashed during an actual landing attempt. That is not what happened here. No astronauts, no active lunar lander, and no ongoing SpaceX lunar mission were involved in this impact at all. This was a leftover spent piece of rocket hardware from a mission that had already completed its primary job over a year earlier, drifting in an unplanned orbit until gravity eventually pulled it down onto the lunar surface. Both of the actual lunar landers that this same rocket originally carried, Blue Ghost and Resilience, had already completed their own separate missions, one successfully, one unsuccessfully, more than a year before this particular impact even occurred. Understanding that distinction matters, because it changes the story from a dramatic mission failure into something more accurately described as a fascinating, if unintentional, natural experiment in orbital mechanics and lunar impact science. Nobody planned for this specific rocket stage to end up on the moon, but once astronomers realized it was going to happen anyway, the scientific community made the most of it, turning an unplanned outcome into a genuinely valuable, well-documented data point. It is also a good reminder of just how much unseen, ongoing work happens quietly in the background of the modern space industry. For every dramatic rocket launch or successful landing that makes headlines, there's a long tail of leftover hardware, spent stages, discarded fairings, and retired satellites that mission planners and independent researchers have to keep thinking about long after the original mission officially ends. Most of that hardware eventually burns up safely, drifts harmlessly, or gets deliberately deorbited according to plan. Every once in a while, though, a piece slips slightly outside those expectations, drifting somewhere unplanned, and it falls to dedicated trackers to figure out exactly where it is headed next. This event is a clear, well-documented example of that quieter, less glamorous side of spaceflight actually working the way it is supposed to, catching an unexpected outcome early enough to study it properly instead of being caught off guard. Looking forward, this event is likely to become a small but meaningful case study in the growing conversation around space debris management, both in Earth orbit and increasingly in the region of space around the moon as well. As more private companies and space agencies send hardware toward the moon in the coming years, including much larger planned missions under programs aiming to eventually return astronauts to the lunar surface, having reliable systems in place to track, predict, and manage the eventual fate of spent rocket stages and other leftover hardware is only going to become more important. This impact, while completely harmless and fully expected by the time it actually happened, is a small but clear signal of a challenge the entire space industry is going to need to keep addressing as lunar traffic increases. Several other companies and space agencies already have missions planned or underway that will only add to that growing traffic. Multiple commercial lunar landers are scheduled to attempt landings over the next couple of years, alongside larger government-led programs aiming to establish a more permanent human presence near the lunar surface later this decade. Every one of those missions will eventually leave behind its own leftover hardware in some form, whether that is a spent upper stage, a discarded landing structure, or eventually retired equipment left behind once a mission concludes. Building good habits now, clear tracking, transparent public data, and early collaboration between companies and independent researchers is exactly the kind of groundwork that makes events like this one manageable curiosities rather than genuine hazards down the road. Before we wrap up the science side of the story, if breakdowns like this, grounded in real tracking data instead of confusing headlines, are what you come here for, take a second and hit that follow button now, because we cover confirmed developments like this one as soon as the real data comes in. So, to bring this all together simply, back in January of 2025, a SpaceX Falcon 9 rocket launched 2 separate lunar landers toward the moon, one of which landed successfully and one of which crash-landed due to a technical failure. The rocket's spent upper stage, however, was left behind in an unstable orbit around Earth, and instead of safely burning up in the atmosphere the way these stages typically do, it drifted for well over a year before its path finally brought it into a collision course with the moon. In April of 2026, an astronomer specializing in tracking exactly these kinds of objects correctly predicted the date, time, and location of the eventual impact, months before it actually happened. Then, in the early morning hours of August 5th, 2026, that prediction came true, as the roughly 4-ton stage slammed into the lunar surface near the Einstein crater at more than 5,000 miles per hour, carving out a crater roughly 60 feet wide. Telescopes on Earth and an orbiting spacecraft near the moon both captured real, verified data from the event as it happened, giving scientists a genuinely rare opportunity to study a predicted lunar impact in real time rather than discovering it after the fact. NASA confirmed there was never any danger to Earth, and researchers are already using the data gathered from this event to better understand impact physics on airless worlds, and to improve how future pieces of drifting space hardware near the moon can be tracked and predicted before they eventually come down. That is the real story here, grounded entirely in verified tracking data, real telescope observations, and official confirmation from NASA and the international teams who watched this unfold in real time. If this gave you a clearer picture of what actually happened instead of the confusing headlines floating around, go ahead and follow this channel, because we are going to keep tracking every confirmed development in space exploration as the real data continues coming in. Drop a comment letting me know what surprised you most about this story, and share it with someone who would find the real explanation more interesting than the confusing version making the rounds online. We will see you in the next one.